Hello and welcome to another part of numerical analysis. In this part, we shall discuss about Euler's method to solve ordinary differential equation. Let us assume one first degree first order ordinary differential equation. Let us consider this equation dy dx equal to fxy, where f is a function of x and y. So this is a first order first degree equation. If this equation is non-linear, then we can only solve this equation by numerical approximation. If we consider one initial condition, that is y x0 equal to y0, then this becomes one initial value problem. So in this part, we shall learn how to solve this initial value problem numerically by Euler's method. So this is the given equation and this is the given function. The functional value of y at the point x0 is given, which is y0. We have to find the value of y at some other point, call it xn. So when x equal to xn, then we have to find y. That means the value of y is given at x0. So value of y at x0, which is y0, it is given. We have to find the value of y at the point xn. So value of y at the point x0 is given. We have to find the value of y at the point xn. To find this value, we first divide this interval from x0 to xn into n equal subintervals. Suppose we are dividing these intervals into n equal subintervals by these points x1, x2, x3, etc. such that the distance between two consecutive points is h. So h is the distance between two consecutive points, or h is the length of each subinterval. So that x1 will be x0 plus h, x2 will be x1 plus h, etc. So xr in general, xr will be x0 plus rh. So xn equal to x0 plus nh. So we are dividing the interval x0 to xn into n equal subintervals. Now in Euler's method, we first compute the value of y at the point x1 first. Then using this data, we find the value of y at the point x2. So if we call the value of y at the point x1 as y1, then using this data we find y1. Once y1 is found, then using this data we find the value of y at the point x2, which is y2. And continuing in this way, we successively find all the values of y at these points x1, x2, x3. Ultimately, we find yn. Now in this Euler's method, we find the value of y1 at the point x1 by integrating this differential equation. So if we write this differential equation like that, dy equal to fxy dx. Now to find the value of y1, that means to find the value of y at the point x1, we first integrate this equation with respect to x between x0 and x1. So if we integrate this equation between x0 and x1, then from the left hand side we get y. So y at the point x0 at the point x1. This will be equal to. Now this is a function of x and y. Actually, fxy, this function varies between x0 and x1. But in Euler's method, we shall assume that the function fxy remains constant between x0 and x1. We shall assume that the functional value in this range is f x0 y0. So we assume that between x0 and x1, the value of fxy remains constant, which is x0, which is fx0 y0. So if we integrate this between x0 and x1, then this will be y at x1 minus y at x0. So y at x1 is denoted by y1 minus y at x0 is y0. This value is given. Now if this is a constant, then we can take this value outside the integration. So if we take this value outside the integration, then it becomes dx from x0 to x1, which is nothing but x1 minus x0. From here we find that y1 equal to y0 plus x1 minus x0 is h. So it is h into f x0 y0. So using this formula, we can easily find the value of y1. Since x0 and y0, these 2 points are known, the function fxy is known, so we can easily compute the value of y1. Now once y1 is obtained, then we shall again apply this formula to find y2. And in the next part, we shall assume that the functional value fxy remains constant between x1 and x2. And the value of fxy between x1 and x2 will be fx1 y1. So if we assume that fxy remains constant between x1 and x2, then we shall obtain that y2 will be equal to y1 plus h into fx1 y1. Now once y2 is obtained, we can easily find y3, y4, y5, etc. So ultimately we shall get yn. So yn will be equal to yn minus 1 plus h into f xn minus 1 yn minus 1. In general, the iteration formula can be written as yk. This will be equal to yk minus 1 plus h into f xk minus 1 yk minus 1. So using this formula, we shall find yn by applying this formula successively. So this method is known as Euler's method. Next we shall give one example. Let us consider this problem. Solve the following differential equation by Euler's method to get y 0.2 from the given equation. This equation is given dy dx equal to x plus y, y0 equal to 1. So the value of y at 0 is 1. So we assume that fxy, so the function fxy is given, it is x plus y, x0 is 0 which is given, and y0 is 1. We need to find the value of y at the point x equal to 0.2. That means this is x0, this is y0. Now this is x0 equal to 0, this is y0 equal to 1, and we have to find the value of y at the point x equal to 0.2. Now here h is not given, that means the length of the subinterval is not given. So first we shall assume that the length of the subinterval is 0.1. So if we assume that h equal to 0.1, then this point will be x2 and this one will be x1. This will be equal to 0.1. So x0, x1, x2. Now using this data, we shall find the value of y1 at the point x1, and then we shall find the value of y2 at the point x2. So we need to find the value of y2. That is the value of y at the point 0.2. That means at the point x2. We know that the formula is y1 equal to y0 plus h into f x0 y0. That is equal to y0 plus h into, now fxy equal to x plus y. So fx0 y0, this will be x0 plus y0. Now y0 is given, which is 1, plus h is 0.1, x0 is 0 and y0 is 1. So we can find that this is equal to 1 plus 0.1 into 1. That means it is 1.1. So this is the value of y1. So here we have obtained that y1 is 1.1. Now if we apply this formula again, then it will be y2, this will be y1 plus h into f x1 y1. So that is equal to y1 plus h into, now fx1 y1, this will be x1 plus y1, because fxy equal to x plus y. Now y1 equal to 1.1 plus h is 0.1, x1 is equal to 0.1 because this is the x1, 0.1 plus y1 equal to 1.1. So this is 1.1 plus 0.1 into 1.2. So 0.12, that is 1.22. So this is the value of y2. So we have obtained y2 equal to 1.22. So we have obtained this data by assuming h equal to 0.1. Next we shall find this data by considering the step length h equal to 0.05. If we assume that h equal to 0.05, that means we are dividing the interval 0 to 0.2 into 4 equal subintervals. So if we assume h equal to 0.05, then we get these 5 points, x0, x1, x2, x3 and x4. Now this value is given. Now using this Euler method, we shall find y1 and then we shall find y2, y3 and finally we shall find y4. We know the formula as y1 equal to y0 plus h into f x0 y0. That means y0 plus h into x0 plus y0, because fxy equal to x plus y. Now y0 equal to 1. Now h equal to 0.05, x0 is 0 and y0 is 1. So using the calculator we find that this value is 1.05. So we have obtained that y1 is equal to 1.05. Next we shall find y2. y2 equal to y1 plus h into f x1 y1. So by the formula this is y1 plus h into x1 plus y1. Now y1 equal to 1.05 we have already calculated, plus h equal to 0.05, x1 equal to 0.05, this is the value of x1, plus y1 equal to 1.05. So this is 1.05 plus 0.05 into 1.1. We find that this is 1.105. So this is the value of y2. So it is 1.105. Next, using this value we shall find y3. And we know that y3 equal to y2 plus h into fx2 y2. Now this is equal to y2 plus h into x2 plus y2. Now y2 equal to 1.105 plus h, this is the h, x2 is 0.1, this is the value of x2, plus y2 1.105. Now if we calculate this, we shall find that this is equal to 1.16525. Now finally y4. So we write y3 equal to 1.16525. Now if we want to calculate y4, then the formula is y3 plus h into fx3 y3. So this is equal to y3 plus h into x3 plus y3. So this is equal to 1.16525. This is the value of y3 plus h into x3 is 0.15 plus y3 1.16525. Now using the calculator we can find that this is equal to 1.2310125. So this is the required value of y4, that is 1.2310125. So here we have found that the value of y at the point 0, 2, this is equal to 1.22 if we assume h equal to 0.1 and the value of y 0.2. This is equal to 1.2310125 if we take h equal to 0.05. Now which one is the better result? That means if we want to compare between these two results, then we have to obtain the exact solution of the given problem. Now for the given problem, the exact solution can be found as y equal to 2 into e to the power x minus of x plus 1. This is the exact solution of the given problem, dy dx equal to x plus y. Now if we find the value of y at the point 0.02, then we shall get that this value is 2 into e to the power 0.2 minus 1.2. This is equal to 1.2428 up to 4 decimal places. So this is the exact value, that means the exact solution, correct up to 4 decimal places. And these two are the approximate solutions obtained by Euler's method. If we consider h equal to 0.1, then we get this value 1.22, and if we take h equal to 0.05, then we get this value 1.2310125. So out of these two values, this one is closer than this one. So this one is the better approximation of the exact value. So we have obtained the better approximation if we take h equal to 0.05. That means if we consider 4 subintervals, then we get the better result than the case when we consider only 2 subintervals. That means in Euler's method, we shall get better result if we consider more intervals. But remember, as the number of intervals increases, the number of calculations also increases. So this method is Euler's method. So that completes the solution, and with this we complete this part. So see you in the next part. Until then, thanks for watching.